Hello everyone. This session is about satellite payload and applications. Since the first satellite launched in 1957, satellites have grown to be useful in numerous fields of worldwide applications. The early satellites were usually equipped with payloads related to science, telecommunication, and Earth observation experiments. It is here that we pause and recollect an idea proposed by Arthur C. Clarke in 1945 in his essay titled Extraterrestrial Relays. Here he proposes the idea of using satellites for worldwide radio coverage, facilitating long-range communications. It is fascinating to learn that the satellites were envisioned to serve global communication long before the first satellite was launched. So what are we going to learn here? Satellites and subsystems, satellite communication, satellite navigation, Earth observation and remote sensing, and scientific and space study applications. The modern day application of satellites goes way beyond global communication. They are used to serve the purposes of navigation, Earth observation, and also for performing observations and experiments of outer space environments.
What are satellites used for? Satellites are man-made objects put into orbit. They often affect our lives without our realizing it. They make us safer, provide modern conveniences, and broadcast entertainment. Here are some of the jobs satellites do.
The first satellite launched by ISRO in 1975, Aryabhata, was intended to help conduct experiments related to solar physics and cosmic X-rays. Hence, this mission can be classified under missions intended for scientific observations. In the year 1981, ISRO launched APPLE, that is Ariane Passenger Payload Experiment, as an experimental communication satellite whose success led to the launch of INSAT satellite series, marking the birth of operational communication satellites in India. The payload carried by a satellite varies based on the mission objective they are intended to serve. A typical satellite will consist of following subsystems: attitude and orbit control subsystem, electrical power subsystem, payload subsystem, propulsion subsystem, structures and mechanical subsystem, thermal subsystem, telemetry tracking and command subsystem, and application payloads, for example cameras, radiometers, radar, transponder, etc. The payload of a satellite is carefully designed and manufactured depending upon the mission objective a satellite is set to carry out. Based on the mission objective, a payload can be broadly classified into three main categories: space science mission, Earth observation, communication and navigation payloads. Before we go into the detail of payloads, let us learn about the transponders, antenna, frequencies, radiometer and cameras. Transponder. In communication satellites, the payload basically receives, amplifies and retransmits the signals. The signals received are mostly low power and they have to be amplified. A transponder is used to accomplish those tasks in satellites. It has elements like high gain antennas, amplifiers, filters and frequency shifters. So what does an amplifier do? It boosts the signal, or we can say it adds more power to it. A navigation satellite payload would consist of transmitter to transmit navigation signals and atomic clocks to provide precise time measurements. The range of frequencies used by satellites for communication is broken down into several bands. Each of these bands is reserved for specific application, as you can see. The complexity of these payloads also varies depending on the satellite orbit. The signal losses for satellites orbiting in LEO are comparatively minimal and have lesser latency with the ground station transmissions. Hence, the aperture size of their antenna is proportionately smaller in contrast to a satellite orbiting in GEO, that is geostationary orbit. This is a radiometer. Earth observation satellites or remote sensing satellites usually require spectral data collection and imaging of the Earth from space. A radiometer is the most common type of payload used to collect this kind of data. Earth observation and remote sensing operations are performed in the visible, near infrared and far infrared regions of the electromagnetic spectrum. So the radiometers have light intensity detectors that correspond to different specific wavelengths of light from all these regions. And then the data from different wavelengths and light intensities help us study the concentration of aerosols, clouds, and water vapor content in the atmosphere. High-resolution visible cameras are also among the commonly used payloads in Earth observation missions. Satellites designed for scientific missions carry a varied range of payloads. These satellites are intended for performing experiments in microgravity conditions or carrying out space observations. For example, the Stretched Rohini Satellite Series, also known as SROSSC, satellite launched by ISRO in 1992 carried two payloads, namely Gamma Ray Burst, that is GRB experiment, and Retarded Potential Analyzer, that is RPA experiment. The first experiment was intended to perform studies of gamma ray burst phenomenon to understand their origin and nature, whereas the second experiment was intended to characterize the electrons present in the ionosphere. A mission named Gravity Recovery and Climate Experiment, that is GRACE, was launched jointly by NASA and the German Aerospace Center to study the gravitational field anomalies of Earth in 2002. The mission consisted of twin satellites communicating with each other on K-band for microwave ranging. These waves were produced using an instrument called ultra-stable oscillator. By comparing both these missions, we can observe the significance of mission objectives in tailoring the satellite payload. Space telescopes are the popular satellite kinds falling under space science mission satellites. However, space telescopes too would vary with respect to the payload they carry. The payloads of a space telescope are mainly dependent on the region of the light spectrum they are intended to make observations. India's AstroSat satellite contains 5 different payloads to carry out observations in different regions of the spectrum. Can you all give other examples of space telescopes? Based on the major fields of research, the payloads on board a scientific satellite can be classified into the following categories: space geodesy payloads, Earth environment study payloads, astronomical payloads, lunar and planetary observation payloads including lander and rover. Payloads used for space geodesy are equipment like radar altimeters, accelerometers, and SAR. They help in mapping the surface geometry of Earth. Satellite-based Earth environment study means studying the upper atmosphere, ionosphere, and magnetosphere. The common payloads used for such studies are devices like spectrometers, ionospheric sounders, charged particle detectors, etc. Astronomical payloads are mainly about studying the universe by analyzing the different regions of the electromagnetic spectrum and using special telescopes to achieve that. Lunar or planetary exploration landers and rovers generally have payloads to test the soil compositions, cameras to take photographs, and seismographs to understand the inner workings of the planet or moon. Let us explore the communication satellites. Telecommunication is one of the most common uses of satellites. It includes services like television, broadcasting, telephony, and data services. A communication satellite can use a point-to-point, point-to-multipoint, or multipoint interaction configuration. It essentially plays the role of a repeater in the communication link. Satellite-based communications in India became operational since the launch of INSAT series in 1982. Communication satellites can be placed in GEO, LEO or MEO depending on the type of service required. The service can be classified into fixed satellite service and mobile satellite services. In general practice, communication satellites that are sent to be used for television broadcasting, radio broadcasting and telephony falls under FSS and are placed in GEO orbit. Whereas for MSS, the modern mobile communication services involving data communication, video conferencing and messaging can be done either using a satellite in GEO or a constellation of satellites in low Earth orbits. One of the most important type of communication satellites are a group of satellites forming a constellation and providing rich data. Iridium is one of the constellation. It is the first satellite constellation and was made operational in 1998. Since then, many satellite constellation projects have been developed to help make data transmission cheaper and faster. Starlink constellation of satellites is another famous constellation owned by SpaceX, which intends to provide internet facilities globally. This includes connectivity to remote areas. A Starlink constellation is expected to have around 2000 satellites in LEO orbit. You can actually see the set of satellites going like a train in the night time if you know when they are going to appear in your area. Satellite constellation projects are gaining momentum due to increased access to space at cheaper costs. However, such projects face several criticisms by various communities across the globe for causing light pollution in the night sky. The development of satellite constellation projects leads to the accumulation of more satellites in LEO and MEO orbits. This severely affects the ground-based sky observations. Another major concern arises due to the long-term piling of satellite debris in orbit. This poses a serious threat to other operational satellites, including all space stations. The communication services offered by satellites can be broadly classified as follows: satellite telephony, satellite television, satellite radio, and satellite internet. Satellite telephony means the application of satellites for voice calls.
Satellites provide in-flight phone communications on airplanes and are often the main conduit of voice communication for rural areas and areas where phone lines are damaged after a disaster. Satellites also provide the primary timing source for cell phones and pagers. Satellites provide in-flight phone communications on airplanes and are often the main conduit of voice communication for rural areas and areas where phone lines are damaged after a disaster. Satellites also provide the primary timing source for cell phones and pagers.
The large distribution area makes it difficult for traditional cable TV systems to lay down the required coaxial cables, so they rely on satellites to help carry programs from the broadcast center to terrestrial receiver stations, from where they are distributed to the cable head-end stations. This is what makes a satellite cable TV network. In a satellite local broadcast TV network, the programs are not distributed from the terrestrial receiver stations to cable head-end stations. Instead, the terrestrial station broadcasts the received signals using ultra-high frequency and very high frequency microwave bands. The user TV is connected to a directional antenna that receives the signals. Most modern day televisions used direct-to-home or DTH services, which involve the direct reception of satellite signals by the user television system using their own dish antennas. Satellite radios are similar to televisions where high-clarity audio gets transmitted to the broadcasting stations via satellite. Just like in the case of satellite TV, satellite radio can also be categorized into a terrestrial broadcast service and a DTH service. The very famous All India Radio, also known as Akashvani, started its DTH radio services in 2004.
Satellite internet is internet that's from outer space. Well, it travels to outer space anyway. Satellite internet travels more than 23,000 miles, and that's just one way. In rural areas, satellite internet is the best option for high speed. A faster option than dial-up, satellite internet has undergone tons of improvements in technology and infrastructure in recent years. In many places, satellite internet speeds can match those that cable and DSL carriers offer even. But let's get back to the satellite. Orbiting directly over the equator in space. How does it all work? It all starts in your home. When you type in a website URL on your device, the request travels by wire to your satellite dish. The dish is mounted on your home, where there's a clear view of the southern sky. This gives your dish the best sightline to the satellite. Obstructions such as trees or buildings could impact your service quality. Installers take these factors into consideration when they choose a spot. A dish sends your request data to a satellite. This satellite is geostationary, which means it orbits the Earth at just the right speed to essentially stay in one place. The satellite beams your data to a Network Operations Center on Earth. The NOC retrieves data needed for your request, a web page, document, audio file, and sends it back to the satellite. The whole process works in reverse. The satellite sends data to your dish, which then goes to your device. Your web request will travel more than 46,000 miles before it returns. All this takes a fraction of a second.
ISRO has also launched GSAT-3, popularly known as EduSat, in 2004, exclusively dedicated to the education sector. EduSat is employed for catering tele-education programs with an objective to provide access to quality education, effective teacher training, and to supplement curriculum-based learning. This has enabled many students across the country studying in remote schools with limited resources to access quality education. Indian communication satellites exceeded the expectation of Indians. They have reached every household with variety of applications. So communication satellites and its applications include direct-to-home, tele-education, telemedicine, vessel tracking, and various other supporting Digital India motive also. Satellite-based navigation systems have revolutionized the modern world with their wide potential. Their ability to provide accurate positioning and cover a large area makes satellite-based navigation systems more reliable and popular.
Navigation. Satellite-based navigation systems like the Navstar Global Positioning Systems, known colloquially as GPS, enable anyone with a handheld receiver to determine her location to within a few meters.
The principle of operation of the satellite navigation system is of two types: Doppler effect-based systems and trilateration-based systems. Has anyone heard about Doppler effect? We all know about it with train example, ambulance example, right? Similarly, when a satellite gets close to the receiving station, the power of signal is high, and when it goes away from the station, the signal reduces. In this system, the satellite transmit signal contains information regarding its path and time. The onboard atomic clock provides the precise time data for the satellite. The receiver station on the ground measures the Doppler shift patterns in the satellite signals as it passes over the station. This pattern, along with the information on satellite orbit, time of signal transmission and signal reception, is used to determine the location of the receiver station. In this method, a satellite transmitting in one frequency is sufficient for determining the location of the receiver. However, two frequency systems were employed in transit to increase the accuracy for military applications. Trilateration-based systems. It is simply an extension of the Doppler effect-based navigation system, but here Signals from 3 satellites are used to determine the location of the receiver station. If you imagine the distance between the receiver station and the satellites as the radius of 3 spheres, with satellites located at the center of those spheres, then the receiver station will be located at the point of intersection of these spheres. The modern global navigation systems like GPS from USA, GLONASS from Russia, and Galileo from ESA employ the trilateration method for determining the position of the receiver. This is the transit satellite system. The first satellite system explicitly intended for navigation was developed in 1960s by US Navy, called as Transit System or Navy Navigation Satellite System. It was based on the principle of Doppler effect. The US Navy launched 2 Timation satellites to increase the time-ranging accuracy, one in 1967 and the other in 1969. The success of Timation satellites combined with the NNSS system led to the conceiving of a global positioning system. As a result, navigation satellite timing and ranging, that is Navstar GPS, was launched by the US Navy in 1978. The Navstar GPS works on the principle of trilateration. India launched a regional satellite-based augmentation system called GPS-aided Geo-Augmented Navigation or GAGAN in 2001. This was intended to develop and certify a satellite-based augmented system for civil aviation applications. Augmentation is a method of improving the accuracy of the navigational satellite system by making use of other additional reference signal in the calculations. The success of GAGAN paved the way for the development of an independent regional navigation satellite system by ISRO called as Indian Regional Navigation Satellite System or IRNSS. It goes by the operational name Navigation with Indian Constellation, that is NAVIC. The space segment of NAVIC consists of 7 satellites with 3 satellites in GEO and 4 satellites in inclined geosynchronous orbits. Satellite remote sensing is a technology that finds a wide range of applications like meteorology, disaster monitoring and prediction, land cover classifications, and others. They enable data collection over large coverage areas and continuous monitoring of surfaces with frequent revisits compared to other remote sensing technology. All surfaces emit radiations based on their temperature or reflect a certain portion of the incident radiations based on their reflecting properties. Satellite remote sensing, in simpler words, means the collection and recording of information about these emitted or reflected radiations at different wavelengths by the onboard satellite sensors. This information is used to determine various other crucial parameters in different applications. Based on the source of light used for remote sensing, it can be classified into 2 types: active remote sensing and passive remote sensing. Active remote sensing, the satellites have their very own artificial source of radiation which is used to illuminate the region of interest. The radiation reflected or scattered by the region is detected and recorded by the sensors. Whereas in passive remote sensing, these systems are used to detect the solar radiations reflected by the surface or the thermal radiations emitted by the surfaces. They do not use an active radiation source for illuminating the region of interest. Most of the remote sensing applications are based on passive remote sensing. Active remote sensing satellites usually use a microwave or laser-based system as the source of illumination. Satellite remote sensing is also classified based on the region of electromagnetic spectrum used for the study. They are optical remote sensing, thermal infrared remote sensing, and microwave remote sensing. Optical remote sensing finds its application in imaging the Earth in visible regions. The study of vegetation covers the study of water bodies or other applications. Thermal infrared remote sensing is mainly employed for studying the temperatures of different surfaces. The shared and unique value of optical, fluorescence, thermal and microwave satellite data is for estimating large-scale crop yields. Can anyone guess what this is? This is Landsat satellite. Landsat satellite series, a joint program by NASA and USGS, is one of the longest running Earth observation satellite programs. It employs both optical remote sensing and thermal infrared remote sensing for imaging Earth. Indian remote sensing program started with the launch of IRS-1A satellite in 1988. It was followed by a series of IRS satellites dedicated to specific applications like natural resource management, disaster management, water resources information, forest and land mappings. The Earth observation programs in India are overlooked by the National Natural Resources Management System (NNRMS), which is a national level interagency system. It helps conduct remote sensing application in projects at national, state and local levels. The OceanSat satellite series launched by ISRO under the IRS program is dedicated specifically to the oceanography and atmospheric studies. They help measure parameters like sea surface temperature, sea surface wind speed, water vapor content in the atmosphere, cloud liquid water content, coastal circulations, etc. These parameters are then used in marine weather forecasting, monsoon predictions, and studying cyclones. ISRO has also created a geoportal named Bhuvan in order to enable easy access to the remote sensing data by people who want to innovate and develop downstream applications. Outer space contains radiations from all the regions of the electromagnetic spectrum. Earth's atmosphere is opaque to a large portion of the electromagnetic spectrum, allowing only specific wavelengths of the incoming radiations to reach the surface. Also, even in space, we cannot see any wavelength that lie outside the visible region with our naked eyes, but we do have sensors and techniques that enable the detection of these wavelengths. A satellite equipped with these kind of sensors will enable us to observe the universe in different spectral regions like UV rays, gamma rays, X-rays. Such observations are important for us as they help us understand the history, evolution and current state of the celestial systems around us. This is very motive behind the development of space telescopes.
Before the space age, astrophysicists were limited to studying the universe via ground-based telescopes, and so could only use information from the parts of the electromagnetic spectrum that penetrated the Earth's atmosphere. Many of the most interesting phenomena are best studied at frequencies that are best or only accessible from space. Satellite telescopes have been critical to understanding phenomena like pulsars and black holes as well as measuring the age of the universe.
Can anyone guess what this is? This is Hubble Space Telescope. The Hubble Space Telescope launched by NASA in 1990 scanned the skies in the UV, visible and near-infrared regions of the spectrum and captured some of the most spectacular celestial events. The AstroSat was launched by ISRO in 2015. It consists of 5 payloads, namely UVIT, LAXPC, SXT, CZTI and SSM. The first payload allows for observation in the visible and ultraviolet region of the electromagnetic spectrum. The remaining payloads are intended for different studies to be performed in the X-ray regime. It is also called as the first Indian space observatory. Earth's magnetosphere acts as a protecting shield against the incoming charged solar radiation particles. It also helps in keeping the Earth's atmosphere intact and prevents it from erosion by solar winds. Scientific satellites intended for performing magnetospheric studies help us get better insights into their development and behavior. Scientific satellites are also sent out as orbiter missions to other planets to explore their surface compositions and atmospheres. ISRO's Chandrayaan missions are among such orbiter missions that were sent to explore Earth's moon. The Mars Orbiter mission, also known as Mangalyaan, is another mission sent by ISRO to study the Martian features. Future missions include Aditya to study the Sun, Venus mission, mission to study exoplanets, human space mission, and space recovery module. Thank you.